this video, I'm going to look at some of the pre-calculus algebra concepts that we could call the basics of functions and their graphs. We'll start with the list of objectives for this section. Our objectives are to use multiple representations of algebraic, graphic, numeric, and verbal, multiple representations of different function types to describe relationships between quantities. And also, by the end of the section, students should be able to investigate the patterns and relationships present in multiple function types: linear, quadratic, exponential, log, rational, piecewise, absolute value, using appropriate tools and representations. So let's start with this big idea of this notation. We're probably familiar with this notation with parentheses, but parentheses can mean a number of different things. Now, if I were to do this problem by the order of operations, I'm going to do the 7 plus 3 first, and then I'll do the 7 minus 2, because we do the adding and subtracting in whichever one comes first. But if I insert parentheses here, it's going to mean, okay, by the order of operations, I'm going to do the 7 minus 2 first before I do the adding. That's one use of parentheses. Another way that we've seen parentheses is with an ordered pair. So this use of parentheses where we see a 7 comma negative 2 in the parentheses, completely different from the first. And then we'll look at a third example of parentheses, and that's where we are now with f of x. F of x. We'd read this f of x. It doesn't mean f times, like we saw in the first example. It doesn't mean f times x, and it's not a notation of an ordered pair. It's simply f of x. It's function notation. It's important that you understand what this notation means and that it has to do with a function, not order of operations, and not multiplication, and not an ordered pair. So let's look at what a function is. To start with, you can see the definition of a relation, and the definition of a function rests on the definition of a relation. A relation is any set of ordered pairs. The set of all the first components of the ordered pair is the domain of the relation. The set of all the second components is the range. So when I look at this first example, the domain would be the set 3, 4, because when I look at the first component, we have 3s and 4s. I'm not going to list the 3 or the 4 more than once, even though they appear more than once. The set includes 3s and 4s. The set of the range includes 4s and 5s. And this is a relation because it's a set of ordered pairs. So we'll start with that. Now, there is a special kind of relation. Some relations are a function, and a function is a relation in which, right here, every element in the domain pairs to exactly one element in the range. You might also read that sometimes it's paired to one and only one element in the range. So every x has exactly one y. There's never an x without a y, and there's never an x with more than one y. Now, when I look at this example, I could see that the 3 pairs to a 4 and also a 5. But when I look at the 4, 4 is also paired to 4 and 5. Notice that we're okay with the first requirement of a function, that it's paired to one element in the range, so there's no x without a y. However, it falls apart with the only one because the 3 is paired to 2 elements in the range, and the 4 is paired to 2 elements in the range. So what we would say is that this is not a function. Let's look at another example. When I look at this example, I can pull out the domain and the range. The domain includes -3, -2, -1, and 0. And the range includes -3, -2, -1, 0. Now, the problem isn't that a 0 is both in the domain and the range. That's not a problem. But when I see how these pair up, I can see that a -3 pairs only to a -3, and the -2 pairs only to a -2, and so on. So if I were to pair these up, -3 goes to -3, -2 to -2, and so on. Oh, it looks like I got distracted and wrote those repeated instead of the -1 and the 0. But we can see that every element in the domain each has exactly one element in the range. So this is a function. You could see other examples in your book, and it would probably be beneficial to look at those. What we're going to do next is solve the equation for y and then determine if it's a function or not. And one way to determine if an equation is giving you a function is to graph it and see if it passes the vertical line test. Now, the vertical line test says that when we pass a vertical line over the function at every point in the domain of the function, that it doesn't hit the graph more than one point at a time. We'll look at some examples soon. But for 3a, what we're going to do is solve for y. So to solve for y, that means I'm going to subtract x squared from both sides. And I'd have y equals the opposite of x squared plus 16. And if we think about the x's and y's, 3, when x is 3, is there more than one way to get a y? So if x is 3, y is going to be the opposite of 3, so -9 plus 16. Or in other words, it's going to be 7. Notice that there's only one answer to that. There's only one value for the opposite of 3 squared plus 16. It's not sometimes 7 and sometimes something else. So for each value of x, there is one and only one y. So we would say that, yes, this is a function. Let's look at this next one, and maybe sometimes seeing the counter example makes it a little more obvious. If we solved this for x, or for y rather, we'd have to take the square root of both sides, but when I take the square root of x, I'd have to do the plus or minus, right? Let me write it like this, just to make sure everyone's clear. If I just reverse them to have it y squared equals x, and then remember with the square root property for solving quadratics, I take the square root of both sides. The square and square root undo each other. But I have to be mindful that there are two answers. There's the positive square root of x and also the negative square root of x. So I can see that this is not a function because there's two values of y. So there's an example of a function, an example of not a function. If g of x is x squared plus 2x plus 3, evaluate g of negative 1. Here's what I'm going to encourage you to do for each of these. Number one, for each example, as you're doing this for practice, I would encourage you to write the function. Now, I know it seems maybe a little redundant for me to be writing it on this example because I have the function on the same page, but you are usually doing an example without the example already, without the problem already printed on your page. So you might be reading the example from the screen, but on your paper, I'd encourage you to write the function. Next, I'd encourage you to rewrite that function, but put an empty parenthesis for every x. I'm going to write it twice. In your example, you wouldn't actually write it twice, but you would write what I'm advising that you do is write the function and then write it one time with those empty parentheses. The third thing you'd do, and let me be clear that you wouldn't need to rewrite it here, but I just want to leave it this way so that you could, going back, see where everything came from. The third step is going to be to fill in every empty parenthesis with the number we're given. In this case, it's negative 1. So g of negative 1 is equivalent to the square of negative 1, which is 1, plus 2 times negative 1, plus 3. And then the last step is going to be to simplify. So when I simplify this, I'd get 4 minus 2 or 2. And that's the final answer. Let's try another one. This g of x plus 5. First, I'm going to write the function. And then I'm going to let me write that correctly. So first I'm going to write the function g of x equals x squared plus 2x plus 3. Next I'm going to rewrite it, leaving an empty parenthesis for every x. I did this one a little bit bigger. I left the space a little bit bigger because I've got a bigger expression that I'm putting in there. I'm going to replace this one with x plus 5. So I'm substituting the x plus 5 in for each empty parenthesis, and now I'll simplify. So step 1, I wrote the function. Step 2, I had the empty parentheses, and then step 3, filled it in. Step 4, I'm going to simplify. X plus 5 squared. Now off to the side, you could FOIL that if you need to. I'm going to use a special binomial pattern, and remembering that a plus b squared is always a squared plus twice the product of ab plus b squared. If you're familiar with that pattern, you could use that shortcut also. Don't forget to distribute the 2. So it's 2x plus 2 times 5, and then plus 3. And the last step is going to be to simplify this. So it looks like we've got x squared, combining like terms, 10x and 2x is 12x, 25 plus 10 plus 3 is going to be 20, 38. 25 plus 10 is 25, is 35, plus 3 more is 38. So I've got g of x plus 5 is equivalent to x squared plus 12x plus 38. Can't stress enough how much I'd encourage you to use those steps each time. And here, let's try it one more time. We've got g of x is equivalent to x squared minus 2x plus 7. So I'm going to rewrite it, putting empty parentheses for each x. And then I'm going to go back and fill those parentheses in with this opposite of x. Last, I'll simplify the opposite of x squared. Just a side note, the opposite of x squared is the opposite of x times the opposite of x. So that's going to be positive x squared. If I had it like this without those parentheses, it would be negative still, right? But when I'm putting that opposite of x in parentheses, it becomes more obvious that it's positive. Negative times negative is positive plus 7. So g of the opposite of x is going to be x squared plus 2x plus 7. We could look at the next problem, graphing, but I'm going to pause here and we'll resume with example 5 in the next video.